For Hermitian and skew Hermitian, I have a way to order. But what about unitary? Now here I take a special case. Now see, basically the thing is, one thing that I'm now stuck to that, oh, if I have a way to order, maybe I have the Wiles type inequality. So now I'm looking for ways to order the eigenvalues, and I realize that if, for example, I have that my all eigenvalues of a unitary matrix will be on the unit circle. Now, if, for example, my eigenvalues are all in one semicircle, whatever semicircle, it need not be the upper semicircle or the lower one or any semicircle, then, so for example, you can see this small image. So this thing. So now I can just start with in one direction. From one direction, I can start with where my semicircle starts. So in the counterclockwise direction or the clockwise direction. And I have a way to order. Now you can say that, okay, why you're looking at, so this semicircle gives me that which, now you can say that this way I can order the thing is that then there won't be, if I say that there will be n matrix has n eigenvalues. So there will be always a small arc. Why semicircle? There will always be a small arc where my eigenvalues are not there. Just draw two chords and then have the eigenvalues starting from there. First of all, it will not be unique, and there will be a problem with the result, with the proof that I will be giving here. So, okay, let's see what is the significance of the semicircle. One way that semicircle helps me is clearly in ordering. And now as a convention, so it's nothing special with counterclockwise or clockwise. I just fix that I will order in counterclockwise direction. That we generally do in, so our orientation in complex analysis also was in the counterclockwise direction. So here now again, I have this beautiful thing that again the Wiles type inequality holds for if A and B are unitary matrices with their eigenvalues lying in one semicircle. So both there is one single semicircle. It can be any semicircle, not, I'm repeating the theme, but there is exactly only one semicircle in which both the matrices have their eigenvalues. Then I order them in counterclockwise direction, and I know that my mod of lambda, again the same kind of thing will happen. So I hope I'm the same with the same slide. So now how will we do that? Just a minute. Yes. Okay. So this is So basically we have the same result here as what we have in the Wiles perturbation theorem. So now to prove this, basically again, we will use that two subspace dimension results, so the intersection of the subspaces, but in a slightly different, now we will use it, but the application will be slightly different, it will be very similar. Now it comes to a little kind of a geometric thing. What we have? So we denote by MAX the number of eigenvalues of A counting multiplicities then in X. So if, for example, I have eigenvalue of X is the set, so let's say X is a set of the interval 1, 2 and close interval 1, 2, and I have eigenvalues of A as 0.5 and 1.5 with multiplicity 2. So then in that case, it's a 3 cross 3 matrix. Then MA of 1, 2 would be 2. Now, my proposition tells me that if I have two unitary matrices, two normal matrices, and K and KB are two post-convex subsets of C, such that, so now I have that my Ka and Kb. So Ka contains K eigenvalues of A, and Kb contains at least n minus K plus 1 eigenvalues of B. So MAKA is equal to K, MBKB is greater than equal to n minus K plus 1. Then in that case, and I have distance between K and KB. These are two close convexes. So obviously they are, now it's delta. We'll take obviously delta to be greater than 0, otherwise it's trivial. So K and KB are clearly disjoint, what we're taking. And distance between K and KB, let's denote by delta, the distance. So then my proposition tells, so then it says, so delta is less than equal to norm A minus B. So the distance between K and KB, where K and KB are two convex sets, one containing K eigenvalues of A and the other containing at least n minus K plus 1 eigenvalues of B, and have distance, the distance between them will be less than equal to norm A minus B. So as soon as we hear that MAKA is equal to K, MBKB is greater than equal to n minus K plus 1, I know what I'm looking for. So again, I'm looking for, in this case, in the subspaces spanned by the eigenvectors, and I will have that intersection to be non-zero. Again, the same thing. So, but how will we be using this? Again, it's an interesting thing. It's so different thing that we, so here, again, so that's a usual thing we expect. Let M be the subspace spanned by the eigenvectors corresponding to eigenvalues of A contained in Ka. And similarly, N be the subspace spanned by the eigenvectors corresponding to eigenvalues of B in Kb. Now, so just here, so A and B are normal matrices. So for students who are attending, my question is, just check here, where are we using, at what points we are using normality. And so, and are we using here, really here, anywhere that the algebraic multiplicity is equal to geometric multiplicity? So just check it for yourself. So so observe the proof carefully. So now by our lemma 1, we have, there exists a unit vector x belong to M intersection M. So my dimension M will be equal to K, dimension N will be greater than equal to N minus K plus 1. Now, I have some special assumption here. Ka and Kb are convex. Now, so let U1 till UK be the orthonormal eigenvectors of A spanning M. Okay. Then, now, so, and let lambda 1 till lambda k be the eigenvalues of A contained in K. So it has K eigenvalues, Ka. So then I know that. So let's look at my X is in M. So X will be a linear combination of U1 till UK. So X can be written as summation AI UI, I from 1 to K. Again the same thing. Now X square is equal to summation mod AI square, that is equal to 1. That also I have. So now look at X comma AX. What is this? We have calculated enough times. So that will be summation AI mod AI square lambda I from 1 to K. Now see, lambda i's are not in any, these are have absolute value 1. These are in the semicircle. So just that. Okay. So now, sorry, so not the semicircle, sorry, Ka. So now what is this? X comma Ax is summation mod Ai square times lambda I, where summation mod Ai square is equal to 1. What does it tell me? Now here, correct convexity of Ka here. Lambda i's are contained in Ka. Ka is convex. And what is X comma Ax? It's a convex combination of lambda i's. And because it's a convex combination of lambda i's, I have that my Ka is convex implies my X comma Ax belongs to K. Similarly, my X comma Bx belongs to KB. The same thing, the same kind of problem. We don't need to repeat. Now, Ka and Kb are delta distance apart. Xax, what is distance between two sets? It's the infimum of mod X mod A minus B, where A belongs to Ka, B belongs to Kb. So that means an Xax, Xbx belong to Ka and Kb respectively. So what do we have? Delta, which is equal to distance between Ka and Kb, is less than equal to mod. So mod Xax minus Xbx. So that means now delta is less than equal to mod Xax minus Xbx. That is equal to mod X. It's linear in, so A minus B X. Now what is this? So this, now we know that this is less than equal to, so my maximum, so this is less than equal to my norm of A minus, and that's it. So I have, because my X is a unit vector, so I have this. So again, exercise for students. Where is the normality? So where the fact that A and B are normal matrices of A and B used in this proof. Now we come to our proof of the main result. So what was it saying? It's basically the Weiss type of inequality, with our ordering being in the counterclockwise direction in the semicircle. So what I have, let's take. So I'm looking at, so let us have that let epsilon be the distance between, so will be maximum of mod alpha j minus beta j 1 less than equal to j less than equal to n. Alpha j's are eigenvalues of A, remember, in the semicircle, arranged in counterclockwise direction, and beta j are eigenvalues of B arranged in the counterclockwise direction. A and B are unitary, so they have, so this you can see. So now let K be the index such that my mod alpha k minus beta k maximum, so it is attained somewhere, is equal to epsilon. Okay. Now that means, so now look at the figure here. So alpha 1 till alpha k. So alpha 1 till alpha k will be above this semicircle and on the right side of this straight line, vertical line. Similarly, now beta k. So alpha k and beta k. So let's assume that we can, without loss of generality, we can assume that alpha k is on the right of beta k. So the way I have shown in the figure. So then what is basically this? So now what is epsilon? Epsilon is just take these two parallel lines. The distance between these two parallel lines is epsilon. Now what I have? So let's take, so we want to apply our proposition 6. So let's take Ka. So proposition 6 asks for two convex sets. Can you guess what will be the convex sets now? The convex set, so here on the right of this line, I can have convex set, this is Ka. And on the left of this line, I can have Kb. So my Ka and Kb become convex sets. And what I know about Ka and Kb, so Ka and Kb I've denoted in the figure. So Ka and Kb I can denote, and what my Ma of Ka would be equal to K, and Mb of Kb will be equal to n minus k plus 1. And what is the distance between Ka and Kb? Distance between Ka, Kb is equal to epsilon. The way we have defined Ka and Kb. And then what does the proposition 6 tell me? That my epsilon is less than equal to norm A minus B. And what is that? That is the maximum of mod alpha j minus beta j. And we are done. So it really basically looks the play of ordering and to choose our subspaces in a nice manner. And then it varies. So we have seen three major proofs, three major inequalities. One for Hermitian, one for Hermitian and skew Hermitian, and one for unitary. In both the things, the common thing was we have some way of ordering. In both in all the three cases, it was just different. But nevertheless, we had some way of ordering. We had some way of having two subspaces and getting a common vector in the two spaces. And then we were manipulating that. Now, there was a question that do all unitary matrices, so for any given unitary matrix, will there be a semicircle where the eigenvalues lie? No, absolutely not. That is an assumption that we are having. So in general, I cannot say. I can have so as I gave the example, any n cross n matrix, take this, just take 4 cross 4 matrix with the eigenvalues 1 minus 1 I minus I. So definitely this is not the case. Then what do we do? Do we stop here? No. Now here we will change our strategy. If I don't have such a thing, so now one exercise here, in fact, before we go further, I want you to see from the proof where have we used. So exactly the semicircle. In the proof, where do we use the fact that the eigenvalues of A and B lie in one semicircle? That is the exercise. So if you get these answers, you know that you understand the concept very well. Okay. So now the question is, what in general? So now here, in general, for unitary matrices, for normal matrices, we cannot think of a ready-made way to order the eigenvalues. So then we make a concession. We don't go chasing to find ways to order eigenvalues. We say that okay, let's not order them. Let's consider them as unordered tuples. So now we come to this lambda is the multisets. We still have, so we are not dropping the condition of multiplicity. We're still taking into account multiplicities, but we are now okay with not ordering them. So in that case, we are working with not Cn. We are working with the space of unordered tuples. So in that case, so now see, if I have unordered tuples, so so if we have one, so if we have unordered tuples, in that case, for example, if I have 1, comma 2, comma 3, then if I'm not considering the order, then 1, comma 2, comma 3 is same as 3, comma 2, comma 1 is same as 1, comma 3, comma 2. So what we are doing, we are identifying all the tuples which are permutation of each other. So that means we are considering an equivalence relation. So now we denote by C and sim. So sim, why I took sim is basically stands for symmetric. So so C and sim. So there we denote the set of all unordered n tuples by C and sim. So unordered n tuples, we can also say that there's multi-sets of n complex numbers. And what is basically that? As I said, this is nothing but the set of equivalence classes. So we define a relation x is related to y if my y each, so y there is a permutation tau such that yj is x tau j. So so now that means I get y by permuting the components of x. And this is an equivalence relation. So my C and sim is nothing but the quotient space of Cn under this equivalence relation. And because of that, so we can get, because it's a quotient space, it inherits a natural quotient topology. Also, I can now define a metric on C and sim. So this is basically minimum of all. So D, I denote by D. This now it will play an important role in this in this lecture, in the coming lectures. So this we call as the optimal matching distance. So this is the minimum over all permutations and maximum over J. So some not so xj minus y sigma tau j. So minimum, so maximum over all j and minimum over all permutations. So basically, we just take the distance between the 10 tuples with all the permutations and take the minimum of overall permutations. So this is the optimal matching distance. So now here, again, an exercise in basic metric spaces that this D what I have defined, optimal matching distance only. So one should obviously verify that it's actually a metric on C and sim. So it's a nice exercise for students to attempt. Also, the quotient, the topology, every metric induces a topology on the space. So the topology induced by the optimal matching distance is same as the quotient topology on C and SIM with this. So I'll give you a very strong hint that almost gives away the whole thing, that why is it so. So let's recall what is the quotient topology. We have the quotient map. So this is a map from Cn to Cn sim in this case. So all n tuples, so it takes n tuples z1 till zn, going to the multi-set, that is the unordered tuple. So it's an unordered tuple, so therefore I'm now identifying the set z1 till zn. So remember, it's a multi-set, it's an unordered tuple. So z1, z2 can be equal. So there can be same numbers repeated. So z1 to zn, ordered tuple going to unordered tuple z1 till zn. So this is the quotient map. How will the open sets of C and SIM with the quotient topology look like? So U is open in C and SIM with the quotient topology if and only if my Q inverse U is open in CN. Now just look at this equality of the sets. So for any alpha, so which is in C and SIM, that is an unordered tuple. So let's take the alpha is alpha 1 till alpha n. The open ball with the optimal matching distance with distance r is this. It looks like this thing. So d alpha beta is less than r, and one can see that this is this equality. It's an easy thing to check out. And as soon as you check this, it's a very simple thing. And as soon as you check this equality of sets, you know that you can easily then prove in a step that the two topologies, the topology induced by the optimal matching distance and the quotient topology, are the same. So we will come back to, in fact, this C and SIM and the quotient topology and so on in our after this also we'll return back again and again to this the optimal matching distance. So now, but one thing that we have so what we prove is now that for two unitary matrices, my du so definitely we don't have that the optimal matching distance is we don't have a way of ordering. So but the optimal matching distance d lambda a lambda b is less than equal to norm a minus b for two unitary matrices a and b. So that is a nice result that we have. So for that, in fact, we so what we are on now, so basically, so we have, so now we will be going to prove this. So again, this for, before that, okay. So as we have the optimal matching distance, so basically what will be our thing? What we are looking for? When I'm talking of minimum over all permutations, and I'm getting, so obviously permutations on n numbers is n factorial number. So I will get a minimum. So I will get a permutation that attains that minimum. How will I get that? So again, there is a very nice combinatorics on this. So what basically we look at? We look at a matching problem. So really finding this permutation is a sort of matching. I have to match with that constraint that it basically attains the minimum. So here, before going into the exact thing, we look at the matching problem. So what is the matching problem? I have two sets of same cardinality. So we are talking of finite sets. So B and G are two sets with n numbers, a number of elements. and R is a relationship. So R is basically a subset of B cross G. What is my question? My question is now, the problem is to find a bijection phi from B onto G such that, so my B comma phi B, that's the graph of my phi, is contained in R. So that means it is a bijection, it's a matching between B and G, and it's compatible to the relationship. So my phi, this bijection is called a compatible matching with respect to R. So this is a compatible matching with respect to R. Now, what does my, so one can see that. So here I define, for given element Bi, I define Gi to be all elements Gj such that Bi comma Gj belong to R. And for I1 till Ik, so Bi1 till Bik, I define Gi1 till Ik to be the union of all Gijs. One can clearly see that if there is a compatible matching, then, so obviously for every Bi, I have a Gj. So in that case, and such that Bi comma Gj belong to R. So in that case, for every compatible, if there is a compatible matching, then the cardinality of Gi1 till Gi1 till Ik is always greater than equal to K. That is very simple to see. What is remarkable is the Hall's matching theorem. So the who are not even in matrix theory would have and done a basic course in graph theory, would have definitely graph theory or combinatorics, would have definitely looked at this result. This is again a remarkable simple result, that Hall's matching lemma or Hall's matching theorem, that tells me that the condition that we were saying it's necessary to see, it's easy to see that it's necessary, is also sufficient. That means given those B and G, the sets with same cardinality, and R a relationship, so R contained in B cross G, I have a compatible matching if and only if my cardinality of Gi1 till Ik is greater than equal to K for every I1 till Ik and K from 1 to n. Again, because it's a little digression, I will just sketch the proof. The proof is basically by induction. For n equal to 1, it's trivial. And I assume for all m less than n, then I prove the thing for n. What do I do first? I first take the case when Gi1 Ik has cardinality strictly greater than K. In that case, so for every I1 till Ik. So this is a special case. It's not necessary that it will hold, but I take this special case first. Then what I have? I can then take some Bi naught and G and some related, obviously it will have somebody related. So Bi naught and Gj naught. Bi naught, Gj naught, they are in R, this ordered pair. I remove this from B and G. So B naught is B minus Bi naught, G naught is G minus Gi, Gj naught. Gi naught. And then because of this special assumption that I have taken, the Gi1 till Ik has cardinality strictly greater than K, after removing these two elements, also my B naught and G naught will satisfy the Hall's condition that we were, the Gi1. So B naught and G naught will have a compatible matching. And together with Bi naught, Gi naught, I have the compatible matching on B and G. Now, so now take the case when for at least one, this I1 till Ik, 1 less than equal to K less than N, mod Gi1 till Ik is equal to K. So that condition does not hold. So is equal to K. Then I take B1 to be Bi1 till Bik and G1 to be Gi1 till Ik. They have same cardinality. They are subsets of B and G. So B and G, because satisfy the Hall's condition, they also satisfy B1 and G1 also satisfy Hall's condition. By induction hypothesis, because K is strictly less than N, by induction hypothesis, B1 and G1 will have a compatible matching. And now one can check that B minus B1 and G minus G1 will also satisfy. So there is a small two-line word in this case that I have therefore I have not mentioned. So B minus B1 and G minus G1 will also satisfy the false condition. There will be a compatible matching between B and minus B1 and G minus G1. Combining B1 G1 and B minus B1 G minus G1, we will have the compatible matching between B and G. So this is now with this thing. So we have a way out to match compatibly. We now give the thing we were expecting for two unitary matrices A and B. My DAB is less than equal to norm A minus B. Here we have totally ignored the ordering. So now, as I said, we have gone beyond to find ways to order. But we still are looking at, when I'm talking of the optimum matching distance, that there is some ordering. But now this ordering is dependent on A and B. Okay, so it's not some universal thing that for Hermitian matrices, for previous cases, what we had that A and that ordering was not dependent on A and B. Where were they having increasing order, decreasing order? Those are not dependent on specifically what are A and B. But here it will change with A and B, the matrices. But there will be some ordering. That's the main part. Now, for this, we again use a similar thing that we use for this the unitary matrices K and KB, a little different way out. Okay, but it's a way, so you'll see how it's though, but how different the proof would be. We will be using this false matching lemma there. So what we have, we are talking of unitary matrices. So will be really now interested in just working in the circle, unit circle. So T be a unit circle, I be an arc on the unit circle, and I take norm A minus B to be epsilon. I epsilon to be the arc, so it will really become the arc. So now if I have I to be this arc, so I epsilon will be, so basically it will be just extension of, so I epsilon is the arc such that the points on I epsilon have a distance at most epsilon with the points of I. So that is the set of all Z in T such that mod Z minus W is less than or equal to epsilon for all for some W in I. Then I say that, in fact, so MA of I is less than or equal to MB of I epsilon. So the number of eigenvalues in I of A is less than, counting multiplicities, is less than or equal to the number of eigenvalues of B contained in I epsilon. So how do we do that? So again, we'll use the same two-dimension subspace theorem. So we're using the same kind of thing. What will we here know now? Suppose that MA of I is strictly greater than MB of I epsilon. So we go by contradiction. That means MB of I epsilon, so or I can write MB of T minus I epsilon. What will be that? So my MA of I. So now let's take that my MA of. So let's take my MA of I is equal to K. Then what can we say about MB of T minus I epsilon? Will be greater than or equal to N minus K plus 1. And now we know that what are we heading towards. So we take, let the same thing, let M be the subspace spanned by the eigenvectors corresponding to eigenvalues. I'm not writing the whole thing now, of A contained in I, and correspondingly n be the subspace spanned by the eigenvectors of eigenvalues of B contained in T minus I epsilon. Okay. Now take the convex combination. So now see. So let's have that. What will be my I? So if I have this unit circle, my I is, let's say this. So my I is, the convex combination will be something like that of I. And I epsilon, so my T minus I epsilon, this is the thing. And convex combination will be this. And this will be my I, convex combination of I. So now, if I take Ka to be this set, Kb to be this set, the convex combinations of I and convex, so convex hull of I and convex hull of T minus I epsilon. Then my Ka and Kb will be at distance epsilon. So my epsilon will be distance between Ka and Kb. Yes. And then what will happen? So now, how many eigenvalues Ka has? A, eigenvalues of A, Ka has? A, K. How many eigenvalues of B, Kb has? At least n minus k plus 1. And now we know the thing. Distance between, so what we get? So now here, what we have shown. So what we have really got now here. So the distance is, so this is. So now see what we have looked at. So this is epsilon. So in fact, epsilon will be strictly less than the thing, because I epsilon, it's open set and my eigenvalues are finite number. So I will have that there is a smaller. So let Kb be the strict contained in the convex hull of T minus I epsilon, and Kb contains all eigenvalues of B that are contained in T minus I epsilon, and Kb is convex. Then what I have? Norm A minus B is equal to epsilon, but this is strictly less than distance between Ka and Kb. And there I have the thing. So now this is a contradiction to our proposition 6. And therefore we get that so I have this thing. Now I come to my main result. So I want to show that there is a matching between, so my DAB, so my D lambda A, lambda B is less than equal to norm A minus B. I have to show that. So basically I have to show that if I have A norm A minus B is equal to epsilon, then there is a permutation tau such that maximum of mod lambda I minus mu tau I is less than epsilon, is less than equal to epsilon. That I have to show. So here I will use this proposition and false matching lemma. How do we do that? So now here, So what I do is, so now as soon as I write the first line, you will get the idea that what I'm heading towards. So let lambda be any subset of eigenvalues of A. Okay, so any subset of eigenvalues, any subset of basically multi, so any multi-set really, or it's subset also. Okay, so any oh, oh no, just a minute. Just slide it to the first slide. So we take lambda to be any set between the lambda to be any subset of eigenvalues of A, and we find, so lambda basically is the multiset here. So, and we write mu of lambda to be the eigenvalues, so that it will be all mu j in lambda b, such that mod mu j minus lambda I is less than equal to epsilon for all, for some lambda I in sigma A or tau A, lambda A, whatever, it doesn't matter here. So for some lambda I in lambda A. So this is mu lambda. This is a set. So now also we look at I lambda to be the set on. So to be all Z in T, which is at a distance. So mod Z minus lambda I is less than equal to epsilon for some lambda I belong to sigma A. Sorry, for lambda I belong to lambda. Here also it's lambda I belong to lambda. Yes. Then what I have? So now see, my lambda, let's say that lambda has eigenvalues lambda 1 till lambda k. Then my I lambda is basically, so for every lambda there will be an arc in T of, so that the points are epsilon distance away from lambda. They can be now disjoint, they need not be disjoint, but so my I lambda is a union of arcs, is a finite union of closed arcs. So I can write I lambda as finite union ij, j from 1 to r, where ij's are closed arcs. In T, ij intersection is is equal to empty for j not equal to x. So that we know, yeah, that we can have. Now what I do is, so if my ij is this, for example, I take my jj to be the set, so jj to be the arc, such that the points, so the points of, so jj is the arc, such that the points of ij, the points of the points of JJ are greater than equal to, are at a distance greater than equal to epsilon from the boundary of Ij. So basically what I was telling, if Ij is this is the inner arc. So now that means my J epsilon is Ij. Also, my mu lambda, the cardinality of mu lambda is equal to MB of, so my mu lambda as I'm taking as the multiset. So MB of, it's, so let me just write, in fact, let me just write here. So let me just write here instead of scrolling down the whole thing so that we can complete the thing. So MB of Ig. So MB of, so now my mod of mu lambda is my mod mu lambda as a multiset. Mu lambda is a multiset. Mod mu lambda is equal to MB of union JJ. Then by the inequality, by the proposition what we had just put before this, I know that my mod lambda at the multiset, so counting multiplicities of eigenvalues of A, mod lambda is equal to summation j I from 1 to j, 1 to r, I from 1 to r, ma of I. So is it clear? Is it ma of I j, which is which is Ij is jj epsilon. So this is ma of, so this is, so now this is ma of I, sorry, this is ma of j, mb of jj, sorry, this is, it just got, so mod lambda is equal to summation ma of jj, which is less than equal to summation mb of jj epsilon. And it's, I'll just write it again. I'll just write it here. So what I have, let's again do the thing. So mod lambda is the inner circle. So now lambda, if we look at, so by all eigenvalues of A, when we are considering lambda 1 to lambda A, lambda k, those are in JJ, union of JJ. So mod lambda will be equal to summation MA of JJ. By the proposition, this is less than equal to summation MB of JJ epsilon. This is equal to, so MB of JJ epsilon. This is summation MB of IJ. And Ij, union of Ij, what is union of Ij? Ij's are disjoint, union of Ij's, what is that? That is so mu I lambda. So this is MB of I lambda. And what is MB of I lambda? This is mod mu of lambda. So what I have got? Mod lambda is less than equal to mod mu lambda. What was my Hall's condition? What is mu lambda? Now, what is my relationship here? My R, now my A and B are the multisets. The eigenvalues of A and the eigenvalues of B. So B and G, what in the Hall's condition? B and G are the eigenvalues of A and eigenvalues of B. And what is the relationship? Relationship is mu I is related, lambda I is related to mu J if mod lambda I minus mu J is less than or equal to epsilon. So this is the relationship. And Hall's condition is satisfied here. So therefore, I have a compatible matching. That means there is a permutation tau such that my mod lambda I minus mu tau I is less than epsilon, is less than equal to epsilon. For I, all I is equal to 1 to n. And there we get that my optimal matching distance. So for one permutation, I have got that my mod lambda I minus mu tau I is less than epsilon, less than equal to epsilon for all I. That means that my optimal matching distance d lambda A, the d lambda mu is less than equal to norm A minus B. So that we get from for all the unitary matrices. In fact, we have that our Wiles type inequality. Now it's not exactly the order, but in the unordered case, the optimal matching distance between the eigenvalues is less than equal to norm A minus B. This is clearly now what happens in the normal matrix. So next now, what we will do is, we will look at the, so we are done with the Hermitian, skew Hermitian unitary case. Now we head towards the normal matrix case, and that is not that simple. We will see that even for a 3 cross 3 matrices, this inequality for normal matrices do not hold. So what now we can do in case of normal matrices, it becomes a beautiful theory that we study for normal matrices. For unitary, everything is settled. But for normal matrices, we actually extend our theory, look at different metrics. We'll see how this connected, and then we will see that, okay, we are not able to get, if we are not able to get with the optimal matching distance, this inequality, Lipschitz continuity, so as to say, or are we able to get Lipschitz continuity, or we are not able to get this inequality exactly. Then at least, do we have continuity of eigenvalues? We started with the weaker notion is that we get n continuous functions of eigenvalues. So now tomorrow we will be looking at what happens with normal matrices, what maximum we can get with normal matrices, and at present what is known for normal matrices. This will also give a glimpse to open problems, a long-standing open problem, and many things to actually still have the improvement in understanding, and the continuity of eigenvalues.